objects collide and scatter off each other. Adding relativity and quantum theory, we find that the energy of colliding particles can lead to the creation of new particles. But the number of particle species is fixed in the theory. This description is adequate for 3 of the fundamental interactions, but it fails for gravity. At the very high energies relevant for quantum gravity, the collision creates extended objects like strings, membranes, etc. Different shapes of a string correspond to different particles, so there are an infinite number of particle species.
A dramatic confirmation of this theory comes from black holes. We can make a black hole from virtually any star. This means that a black hole must have many possible internal configurations, the number fixed very precisely by thermodynamics. When we count the possible configurations of strings for a given total mass, we get exactly the correct number. So, string theory has the right microscopic structure to describe quantum gravity.
A deep idea emerging from string theory is that matter and space are 2 descriptions of the same thing. We can study a complicated collection of stringy matter and note its vibration frequencies. But by Einstein's theory of general relativity, matter stretches space-time, and we can look at the vibrations of this extra space created by the matter. We get the same frequencies, showing that we can replace a description of matter by a description of space.
One may think that there are many ways to make theories with such complexity, but it turns out that mathematical consistency allows only a unique theory. But if the theory is unique, then it must explain all physical interactions, not just gravity. Strings live in 9 space dimensions, but we see only 3, so the other 6 must be tightly curled up. Deformations of these extra dimensions evolve as moving pulses. These must be the particles we see around us. The number of possible ways to curl 6 dimensions is vast, so a random choice gives strange ratios of physical constants, which is just what is observed.
Most exciting would be to apply all this to the early universe, which has high density just like a black hole.
What do you think? Well, explain yourself.